I'm Ash Cleary. I'm a principal at LDV Capital. I am very excited to be moderating today's panel titled Beyond Human Vision, Unlocking the Invisible with Visual Technology and AI. Humans rely on vision to see, experience, and navigate the world around us. We see objects only when they are within a light field created by a light source. The human eye can only perceive less than a fraction of 1% of the entire electromagnetic spectrum. Yet most of the world's 50 billion cameras and visual sensors are still designed to only capture and analyze visible light. Today, we explore how machines see far beyond human vision across hyperspectral imaging, nanoscale visualization, radar, LiDAR, and more. We'll discuss how these modalities capture, analyze, and interpret data that is fundamentally invisible to the human eye, and why that unlocks insights across precision healthcare, environmental monitoring, industrial inspection, and autonomy. With that being said, I'm honored to introduce our distinguished panelists. Professor Dame Molly Stevens, John Black Professor of Bionanoscience at Oxford and global leader in biosensing and regenerative medicine. Ziv Attar, CEO and co-founder of Glass Imaging and former Apple computational photography leader. And Dr. Friedrich Korting, applied geoscience strategist at HiSpect and expert in hyperspectral imaging for mining and resource intelligence. Welcome all. How is everyone?
Great, good to be here.
Very good. Thank you, Ash.
Wonderful. Amazing. Well, it's great to see you all. I'm really looking forward to our discussion, given all of your domain expertise. Let's start with some introductions around the room. Molly, please feel free to start us off, followed by Ziv and then Friedrich.
Okay, hi everyone. Happy to be here. I'm a professor at the University of Oxford. I help to run an institute called the Kavli Institute for Nanoscience. I work a lot on biomaterials, but also on a technique called Raman spectroscopy, Raman imaging, and I'm the founder of multiple companies. So I run a very big interdisciplinary group, and I'm interested in the sort of academic through to the translation. So very happy to be here.
Hi, Ziv Attar, background in optical engineering. Worked on various optics applications, and a lot of them will be relevant to what we're discussing today, which is super interesting. Did lots of defense, consumer electronics, optics, things like that. And then in 2011 started Lynx Imaging, which was later in 2015 acquired by Apple. So joined Apple for 5 years. During that time, my team launched the portrait mode, and which is very familiar for users, but also a bunch of under the hood things like the depth map that's generated by the multi-cameras on the back of the iPhone, and then also the portrait lighting, which is effects that rely on depth from the multi-camera. In 2020, I left Apple and started Glass Imaging, which is the current company working on, and we're focused on how AI can change imaging systems in the very broadest sense. So kind of pure AI approach to image processing.
Great. My name is Friederike Körting. I'm a spectral geologist. I founded a company that is located in the multispectral and hyperspectral greenfield exploration space. And shortly after, that was during my PhD, shortly after I joined HiSpect, which is a company based in Norway. And we make hyperspectral images in the visible to near and shortwave infrared. So we focus very heavily on spectral fidelity and calibration stability. So I'm both feed into the software analytics and also the technology and hardware side of things. I've worked a lot with hyperspectral imaging in the last 13 years, and what I'm most excited about, especially for mining, is that it translates physics into operational decisions. And that's what we're going to talk to, or what I'm want to talk to you guys about today.
Awesome. Wow, thank you all for your introductions. Let's get right into it. To give our audience a little bit more context, the section of the electromagnetic spectrum that is visible to the human eye, aka the visible light spectrum, ranges in wavelength from approximately 400 to 700 nanometers. This means the human eye can only perceive less than a fraction of 1% of the entire electromagnetic spectrum. Approximately 95% of the 50 billion camera systems in the world today only analyze visible light, which leaves immense potential for camera systems and visual sensors capable of collecting exponential amounts of data that exists across the remainder of the electromagnetic spectrum. My first question for all of you: what are the most important blind spots in human vision, and yes, the pun intended, that visual technologies are now starting to unlock, and which industries will benefit first?
I'm happy to to be first.
Go for it, Zir.
So yeah, I think it's an interesting topic. I think before diving into my answer, at least, it's true that the spectrum is around 400, 700 for the human vision, but it's also true that we can't distinguish between two different light sources that are very close together. So there's also an aspect of spectral resolution, which is in that range, but we're still blind to it. And if we weren't, we could see, for example, skin issues, melanomas, things that are still in the visible spectrum, but we can't see and machines can see it. So I think that's part of my answer will be, covering a broader spectrum. And there's many applications in there. If you go up to the near IR and infrared, you can, if you go way up to 3 to 5 micron, you can detect the gas, and that can serve, gas leaks in houses, and you can detect gas from an airplane to find natural resources in nature, which is super interesting. Not necessarily an application for a, let's say, smartphone-like device. But I think your question is like more, what are the challenges in getting devices that see these digital modalities into mainstream consumer applications? And I think it's kind of a chicken and egg problem, right? And if you could do something now, or build a device and go and have Apple and Samsung and all the phone makers integrated their phones, but there's only very specific application, like detecting gas, for example, it's nice, but it's not worth the extra space, power consumption, cost of adding such a component. So I think the barrier for entry for any device that sees, let's say, additional parts of the spectrum or better resolution inside the spectrum is the application. There needs to be major applications in order to launch. And if we look historically in the last few years, like the LiDAR on the front facing on the iPhone, for example, it's used to unlock with the face, the Face ID. That's an application that Apple built internally. So they didn't just build it in order for others to develop an application on it. Same for portrait mode. There's 2 cameras and you have a depth map, but just relying on app developers to use that depth map and make something cool that's going to be used by others, it's kind of a long shot and very risky for a big company. So I think the main problem is to cut the chicken and egg problem and introduce some applications on day one.
Interesting. Molly or Friedrich, what are your thoughts?
Yeah, very happy to jump in. So I'm really interested in how we can use lasers, like near infrared lasers, for example, to measure chemistry. So essentially to measure the inelastic scattering of light from molecules and from cells and from tissues. So we've done a couple of things in that area that I think are really, really exciting. One is we invented a new technique, which is called single particle automated Raman trapping analysis. This is now CE mark approved. It's sold around the world through a company called Sparta Biodiscovery. And that enables us to both measure chemistry, but also to trap particles, small particles, who enable us to measure their chemistry particle by particle in an automated way. So that's one way that we use this to measure chemistry. The other approach that we use a lot is essentially using Raman spectroscopy to image cells and tissues, and that gives us a global biochemical fingerprint of what's going on, and it can tell us all sorts of things about healthy versus disease states and real-time sort of biochemical changes that are happening in those systems.
Yeah, maybe I'll jump in right after you, Molly, because I'm also more in the non-visual context. So I also work mostly with a shortwave infrared in mining. And I think one major blind spot in mining specifically is the lack of material composition that we get from outside of sampling or spot sampling. And hyperspectral from different scales and different platforms actually enables us to identify different materials on site. And now with new computing technology, it also enables us to do that in real time in many applications. So that means that we are actually able to identify how chemistry leads different behavior in our imagery. And we can train AI models based on physical thresholds, which makes it really robust. One example, not only necessarily in grade or efficiency improvements in mining, a big thing is safety improvements. So an example that we have with a customer in open pit mining is that they're using our UAV systems with a miniaturized shortwave infrared camera to detect where swelling clay is expected and where swelling clay appears in a mine phase, which then leads to slope instability. And without hyperspectral, you can only do that through spot sampling and then interpolation. And this is now possible in real time. And we've just finished an EU-funded project where we've made this processing real-time able. So that's very exciting. It's very cutting edge.
Yeah, it's definitely very exciting. I mean, let's dig into each of those different focus areas. And by the way, for the audience, feel free to be putting your questions into the chat throughout. We'll be having time towards the end to get to some of those questions. Molly, as you mentioned, a lot of your great work and research operates at the nanoscale in biosensing. How do emerging visualization techniques help us detect biological signals that were previously impossible to observe? And as a follow-on to that, what breakthroughs could this unlock when it comes to precision healthcare?
Yeah, so I can think of a lot of different ways, I suppose, where this is impacting. So in terms of, I'll talk maybe first about our own research and then more broadly, but in terms of some of our own work, so the Sparta technique that I mentioned, where we can trap these individual nanoparticles and measure their chemistry with the laser, this is enabling us to measure, for example, composition of new types of vaccines, that sort of work, but also we can measure really, really small vesicles or nanoparticles that are released from our own cells. So, for example, from cancer cells versus from healthy cells. And we can use that chemical information that we're getting to enable us to understand where these vesicles are coming from and what stage, for example, of disease they might be coming from. And so that's a really exciting new sort of application that we can do. We've also developed little reporter molecules that you can use within that system to specifically enhance part of the signal that you might be interested in, for example. And so that's one area I think that's very exciting. But you can also use this kind of sensing in a point of care format, for example. So if you wanted to use a test that could detect a particular analyte, like a protein from a virus, for example, then you can use what we would call plasmonic type particles and other particles that can also selectively enhance your signal. And that can give you very, very ultra sensitive biosensing, so much more sensitive than what you would get with a conventional COVID test, for example, that we're very used to seeing.
On that point, Molly, could you elaborate a little bit more on how that applies directly towards point of care? Can you touch on the difference between what we've seen up until now and what this is going to be enabled?
Well, I think what you're essentially able to enable is a higher sensitivity, which means that within a particular biological sample, whether that's a sample of saliva from someone or a small amount of blood, you've got a certain number of particles related to your virus, for example, and you're going to be able to detect more of those with a higher signal within a given volume against a background. And so that's very, very good. On the other hand, you do need to have a more extensive reader system to be able to read out that signal. Because if you are looking, for example, at a standard lateral flow test, again, if I go back to the COVID test that everybody would be very familiar with, where you see that red line from tiny gold nanoparticles, your eye is actually really good at seeing that, right? And if you were looking at a chemical signature, you would have a different kind of reader that would interpret that signal for you.
Okay, great. Well, Ziv, you've successfully shrunk complex optical systems into the pockets of billions. What is the physics wall we hit when we're trying to bring modalities like LiDAR or shortwave infrared into mass market consumer devices?
Yeah, that's a good question. I think probably the biggest barrier is what I mentioned earlier. It's that the existence of the application. The consumer industry is driven by giant companies that we all know, and they have and not just the consumer companies that we know, but their suppliers. So all the manufacturers, they're spread around the world. They're very good at cost reduction, miniaturization of things to the degree possible. So we're talking about sensing or optics, and things don't always, things scale, sensors scale, optics scale, but the wavelength is the same wavelength. So it doesn't matter if we're talking about visible or near IR or UV, the wavelength does not scale. So, and photons also do not scale, assuming we don't have the ability to shine light on them, which in some applications, like Molly just mentioned, you can use a laser. So you're not so much limited with photons. In many applications you are, and that sometimes dictates that you need a very big device. I won't go too much into topic, but let's say generally speaking, a big device in order to get a healthy signal. So you always have at the end of the day a signal and noise problem. You want to see something, but it's covered in noise, right? And I think one of the things that helps push this limit quite a bit is AI or convolutional neural networks, which are very good at finding a grain of sand on a big beach that's slightly different than the rest of the grains of sand. Whereas if you were using a traditional algorithm to do it, I don't want to say it's impossible, but it's not practical. It might take you a year to run a supercomputer or something, but you also need to understand all the logic of why that particle behaves the way it does. In let's say, if we're talking about hyperspectral in many different bands of the spectrum, when you have reliable data for training, let's say ground truth data and measurements, it's kind of disappointing in terms of engineering that you don't need to always understand the problem in order to solve it. You kind of throw data at the problem, but sometimes it does work. Sometimes small changes in the property of a surface or some particle that you're looking at, it has lots of small changes. Historically, academics and researchers have found like distinct points. Like, for example, you take autofluorescence of bacteria. It's known that at this wavelength, it has autofluorescence. You shine light on bacteria with this light, and it emits light on another spectrum. But if you actually look at the spectrum of the autofluorescence of the bacteria, it actually has peaks in different wavelengths, not only one big peak. In using AI, if you're able to have the data to train properly, you can actually capture all these things together without analyzing one by one. So it's kind of a way to speed up research and cover a big spectrum of in this case it's light, but I'm sure this also applies to acoustics and other applications. So yeah, I think the thing that will push it the most, besides cost reduction, shrinkage of components, which is needed if you want them to go mainstream. For some application, things need to be small, like a phone. Things this size cannot go into a phone. And enabling that shrinkage is basically fighting an SNR problem, a signal to noise problem, which AI is very helpful at I wouldn't say solving, but pushing the limits much beyond what you can do without AI.
Sure. And how much is that, how much have you seen that scaling occur over the last 5 to 10 years? Obviously, a lot of these modalities a decade ago were even more cute and niche than they are now, and the ability to train mass data nowadays is much different than what it used to be before. How are you seeing that influence the timeline for improving the signal to noise ratios?
I think we're now at a very interesting inflection point, because not because AI is now more understood or more used. It's because edge devices now have ability to run very complicated models in very short time, sub-second. This was not true 2 or 3 years ago, or it started 2 or 3 years ago. I think going forward, and we're familiar with what some of the silicon companies are going to launch next year and the year after. It's growing exponentially in terms of neural compute capability, and that opens up lots of doors. The other side of it is the more general, GPU industry or machine learning training industry, which allows you to do the training. So inference is one thing on device, and that's growing definitely. And we are at this inflection point where it's becoming so powerful that you can do things that you couldn't do. Even this year, you could do things, and we see it in our company. For example, we were doing still photography, AI raw processing. So taking the data straight out of the sensor, letting AI do everything, demosaicing, denoising, HDR super resolution. We're barely able to do it 2 years ago. Now we can easily do it for stills. And from this year onwards, we can also do it for video. So it just gives you kind of a feel of how the pace of things is going. And this is more conventional imaging, photography and video, but it also opens up possibilities to do lots of interesting things with hyperspectral sensor, or just sensors that are outside of the range. And I think that involves two things. One is capturing the data and making sure it's aligned with the visible range, because for some applications you want it to be aligned. The other side of it is understanding the data. So you can collect tons of data with multiple sensors on a device, but to understand the data and not work on it for 10 years and find this this grain of sand, running it through AI models is very helpful. And I expect things to keep growing exponentially. So I'm sure we'll see applications that we could not dream of today and in 2 years from now.
I'm sure. And later we're going to get into what 5 to 10 to 20 years looks like. Friedrich, I want to loop you in. I know you work a lot in shortwave infrared. You mentioned that in your introduction. What do you see as being the biggest challenges in turning hyperspectral data into decisions that mining or environmental teams can actually trust and act on?
Yeah, so I think one of the big things in mining, but I would argue in every industry, is transparency. So it goes towards building AI models, and it goes towards capturing data. So I think one of the things we've seen in the 80s and 90s, where hyperspectral and multispectral, and specifically remote sensing, had a really big wave of adoption, kind of failed or saw some drop in interest, at least. So now we're in that curve where the cameras are actually getting towards a more affordable, miniaturized format. The mean time between failures, the whole hardware technology side, is very mature at the moment. One of the barriers for mining specifically is the ruggedization, and I think we're on top of the ruggedization is the potential to actually compute on site. Mining has the downside of being in very remote regions that don't necessarily have stable connection. So you need an integrated system that can work on that site with a customized purpose in real time, where you either need very big champions of the technology on site, or you need to have very robust models that can withstand a lot of variability. And I think we're getting towards a point where some of these things are being solved by, for example, providing illumination stability and tests that we see. So for hyperspectral, especially for the shortwave infrared, you need to have stable sun illumination. With a big part of the electromagnetic spectrum that we're interested in is between 2000 and 2500 nanometers. This is where we see the mineral fingerprints. This is where we can draw conclusions and have direct correlation to mineral, but also to like gold mineralization or general metal mineralization. In order to do that, you'd either have to be in the perfect arid Chilean desert that has sunshine all day and night, right? Because mining is a 24-hour business. But we now see that supercontinuum lasers are coming into play, that we have a stable illumination source without any changes in actual illumination, where we can provide really robust and repeatable data collection, but then also data processing. We also see that these hardware sensors are integrated on site with other cameras and other sensors also outside of the visible. For example, laser-induced breakdown spectroscopy, so we can directly link it to chemistry or to mineralogy on site in a relatively short time frame. I already mentioned miniaturization, but that's been a really big breakthrough to actually get cameras onto a drone system to enable longer flight times and reach remote areas. So that has been a barrier, and we're overcoming that at the moment with better battery technology and better rules and regulations around drone use in operational mining, for example. And Australia is a really good example for making that possible and enabling that instead of hindering that adoption. Yeah, and last thing is the edge computing is important as well, even though we're not on a consumer device. It is really important to enable dealing with these quite big data sets, and if we want to deal with digital twins in mining, we need to update these data sets regularly and compute the whole set and stack of data to show that change and lead decisions proactively.
Oh, well, obviously, I'm a bit biased, but I'm glad Australia is setting a great example. I guess you used the term fingerprinting, Friedrich. What are your thoughts on the timeline? It seems like nowadays a lot of sporadic surveys are occurring for mineral exploration. What is your thoughts on the timeline for when the technology you're speaking about becomes an embedded sensing tool that replaces the more sporadic nature of what occurs nowadays?
Yeah, that's I'm obviously biased towards that as well, but I'm really excited about that opportunity because we do see, from a camera developer side, we do see our cameras being used in more embedded systems. They're being used in mining for sorting applications and sensor-based sorting. So they are on-site running 24/7, enabling mine and mine waste differentiation. I think it is a 5 to 10 year time frame. Actually, we're getting closer to it being an adopted system. And we also see systems being used for online monitoring over conveyors to analyze the quality, but also deleterious minerals and contamination. We're using them on crushers. We've tested track bed scanning. Like in mining, there's a lot of different stakeholders and a lot of different interests. And I think that gives a lot of opportunity to offer that as a product. But in the end, we need to find that one stakeholder that will have the first added value to keep it running for 10, 15, 20 years. And one opportunity here is that, as I said before, hyperspectral imaging specifically has been used a lot in the exploration space, and it's being used as a standard tool for drill core scanning. And it has been used for drill core scanning for years now, for decades. If all of that data is kept available and actually used and integrated, when from an exploration project 15, 20 years down the line, you're actually starting and commencing operational mining, all of the data can be integrated into modeling and reshaping the occurring mine planning, not only the deposit model that is built on the exploration data.
Right. Well, let's stick to this 5 to 10 year out time frame and focus on what the next decade of invisible imaging looks like and pushing the frontier of what's cutting edge. In the next 5 to 10 years, for each of you, which sensing modality that is currently quite niche or expensive do each of you believe will become mainstream and widely deployed, and why will that be? Perhaps Molly, would you like to go first with that one?
Yeah, sure. So in terms of the chemical imaging, I think, what's really exciting, and this is starting to happen, but definitely not mainstream yet, is thinking about how you might use these kind of technologies in real time, for example, during a surgery. where you're trying to excise the tumor and actually imaging that tumor margin in real time and understanding where the healthy cells and the tumor cells end. And if you could have that sort of technology within your routine operations setup, that's going to be transformative to how you are able to excise the tumor with just the right amount of tumor margin, without excising too much tissue. So that's one sort of area. Another area that I think has a potential to grow a lot is thinking, of course, around miniaturization, as Ziv mentioned, but how we might then be able to, if systems are really miniaturized, could we wear them potentially incorporated within wearables? Things like sweat metabolite sensing, I think, is really potentially a good substrate to be able to measure the chemistry and changes in that kind of chemistry. So that's very exciting as well. And I completely agree with the points around how AI is impacting on everything. I mean, within our own group as well, we just published a new framework in proceedings of the National Academy of Sciences around using sort of recent advances in machine learning to help us do better Raman unmixing using auto-encoded neural networks. And so that kind of whole AI and different aspects of AI, machine learning, deep learning, etc., we are just seeing impacting on really all aspects of science, I would say, at this stage. So that's a few of the main areas.
I mean, those are only a few areas, Molly. I'm sure there's even that's scraping the surface of what's possible, which is very exciting. Ziv, what are your thoughts to my question?
Yeah, I think just continuing Molly's direction. I think if you look at say consumer mass market devices like phones, but also wearables and glasses, which are starting to pick up, which are on your face and they can do a bunch of measurements, watches, bracelets, whatever. I think there's a lot of things that from a technology standpoint, we can already do today. Like, I don't know if you noticed, but my voice is a little bit off. There's no reason that we do not have some hyperspectral sensor here, and I can check if I have a strep or is it just some virus. So I think like our AI doctor, which will guide us how do we self-diagnose ourselves, will get a lot of tools. And there's many things that you can, like I said, even today with the technology, I'm not saying it's in our devices, but it could be hyperspectral imaging of the retina. You can pick up lots of signals and they're related to glaucoma, to Alzheimer. There's tons of good research that show that there's many things that you can diagnose from many parts of our body, many signals, like Molly mentioned, sweat in the mouth, and even just looking at the skin with hyperspectral imaging, you can learn about a lot about oxygenation levels and other and correlate these things with existing sensors like heart rate sensors, which we already have on let's say smartwatches and some other devices like smart rings and things like that. So I think the more we incorporate these sensors, and I know I kind of focus on medical application, or let's say health, not medical applications. I do think that that's going to be a big jump in introducing more modalities to smartphones and their ecosystem, let's say consumer mass market electronics. And I think it's very exciting. We won't have to wait for everything to go to the doctor. Like for example, melanomas, you can detect them if you can, with some, let's say, not even hyperspectral, but multispectral sensors, you can detect them pretty easily today. And we're not doing it. Like I still go to my dermatologist once a year to see, which is fine, but maybe you can do it once a week or once a month or whenever you want. And of course, it has a big effect on the whole industry, and costs are going to be different. And I think some people might say, oh, it's a bit reckless. But if it's managed correctly on consumer devices, not telling you, you have this, you have that, but at least raise a flag. Okay, you need to go to the doctor to check because you have suspected strep in your throat or whatever. So I do think we'll see a lot of applications related to health. And there's also another side of this outside of the spectrum, the visible spectrum imaging that can actually help a lot for the visible spectrum. I'll give a quick example because I know we don't have lots of time, but let's say that you want to create a really nice RGB image, just a regular photo of your friends in the bar, but there's very little light, right? When you look in different spectrum, it's much easier to illuminate without disturbing. So if you have a near IR camera and a near IR flashlight, no one sees it. So now you have another image which is much less noisy compared to the RGB image, and then you can fuse them to enhance the RGB image. So basically to kind of resolve more and remove noise. So I just want to say that outside of the visible spectrum, there's also applications that can actually help the visible spectrum outperform what it's capable of doing today.
Sure. And we at LDV certainly are aligned on the future of healthcare. Both yourself and Molly are speaking about. We wrote an article titled "Your Bathroom Will See You Now" at the end of last year that I see Evan put in the chat links. So we are definitely on the same page about what that's going to look like over the next 5 to 10 years. Friedrich, how about yourself? Over the next 5 to 10 years, you already spoke about this a little bit for the mining sector. So perhaps is there another sector or another modality that you feel will be mainstream in 5 to 10 years from now?
Yeah, and it's already used in a lot of sectors and will probably become a standard tool there. So I've just seen it in the chat, but visible to near and shortwave infrared is already being used a lot in smart farming, for example, because it's a more predictable industry, and the actual cameras allow us to see chemical change before the visual perception for us is there. So we can detect plant stress or diseases or fertilization, like fertilizer content of the soil, or even water use of the soil, and identify that not only from remote sensing, but also from miniaturized sensors in greenhouses or on trucks. And that's the same for mining, that the miniaturization of these sensors on haul trucks and on stationary stockpile monitoring devices will probably become a really big thing here. We mainly talked about the shortwave infrared here, but I think the midwave infrared, at least in the research space, is quite up and coming, because we, especially talking about lithium and battery raw materials, you do need the midwave infrared to look into lithium-bearing mineralization, for example. And that's just lightly touched upon so far. I think it's coming very quickly, though. So I'm excited about those. And we do work with a lot of different other industries, not only smart farming and mining. We also see that, for example, with textile recycling, there was a change in the European legislation. So now we have a lot of projects into textile recycling to ensure that we get these blended fibers and understand that they're being sorted and reused properly. And that's the same for consumer products and secondary raw material recycling. So there's a lot of really interesting, everything that has to do with material property detection. If we need to scale that and make that faster, hyperspectral imaging in these different wavelength regions is a huge tool for that. It doesn't necessarily give us the same accuracy as geochemistry, but it gives us a very, very fast idea on where to sample and how to verify.
Sure. I think overcoming that trade-off with high volume analysis, yet better accuracy than what we see today, is going to be a huge unlock, especially across any material-based analysis. That could be, food freshness, for instance. I see someone made that comment in the chat. We only have a few minutes left. Unfortunately, I want to ask a final question to everyone. And this is really looking at even further beyond the next 5 to 10 years. I'm talking more 10 to 20 years out. That's bleeding edge. What, in one sentence, would you say is a bleeding edge invisible imaging opportunity that will be possible by 2040? It's a question of when, not if, but it's in that 10 to 20 year span from now. In one sentence, what do each of you think? Come on, Ziv, I see you thinking.
If I had to guess quickly, I would kind of keep going. Same thing I mentioned before. I think medical. So the kind of fast forward in time with development of infinite sensors at our home, on our body, whatever. I think the biggest thing will be like our virtual doctor, virtual health, which you could probably fix most of the health problems of today. I'm sure people 50 years ago thought this would happen in 50 years, but I think we are at a point where it's possible, not so much because of the building better sensors, but because of the ability to understand lots of data together, which is based on AI, of course. So that's my my thinking. Of course, that's just like a major thing that will impact everyone's life. There's also self-driving, robots doing our jobs, and things like that. Maybe some other interesting point. I went to a drone conference recently because we're also doing some stuff for imaging for drones, and I learned that already today, which sounds futuristic, but to me it was kind of new, that big farmers, they use drones to scan the crops daily, pick them up when they're exactly the right ripeness, and also detecting disease on a tomato or whatever, which is 10 miles away, and sending another drone to spray it with the medicine that's needed to cure that plant. So that's already happening today. And I don't know, I thought this was a future thing, but it's already happening. So we're in the future.
just makes you think what's going to be possible in 10 to 20 years, right?
World is moving fast, like Jan Erik said before. It's moving really fast right now. It's interesting times.
Totally. Yeah. Molly, in one sentence, what are your thoughts?
Well, I guess I'm really excited to see the developments that I know will be coming in more robust measurements. So, for example, when we have more enhanced forms of Raman, like surface enhanced Raman spectroscopy, for example, getting better substrates, that are more robust, more reliable, and also approaches that will enable faster imaging. So you can already do much faster imaging, for example, through stimulated Raman scattering and other cars-based approaches, but really increasing robustness and speed, and that will also be things like AI coming into play there to help with those. But that's going to be really key, I think, to be able to use these things in the most facile way possible.
Sure. Friedrich, the final word.
One sentence. So I think I've mainly talked about open pit mining right now, but the actual metal deliveries and the discoveries are deep-seated deposits. So I think getting hyperspectral into the underground is going to be something that's definitely bleeding edge still. But I do see that happening with autonomous trucks and mounted sensors and very clear thresholds and decision outputs that can be used in remote control centers. And some of it is already happening, and it does feel very sci-fi, but I think we're getting even further.
Oh, very cool. Well, that brings us to the end of our time together. I'd like to thank all of our fantastic panelists once again for such an engaging conversation. I know we didn't get around to every question in the chat from our audience, but Molly, Ziv, and Friedrich will likely be sticking around for a little bit. So if anyone in the audience would like to ask further questions in the chat, then I'm sure they'll be able to answer a few of those virtually. We at LDV Capital are very intrigued by the future of invisible imaging and its potential across many sectors. So if you're building or thinking of building in this space, feel free to message myself or our team directly.